Okay. All right. All right. Thanks for joining me here. Today, I just want to come live on TikTok. Oh, my YouTube channel. So that we can dissect some certain matters. Yes. Favor. Good. Now, favor, if you be this. Favor, you're highly welcome. Was it? So. Okay. Okay. I think we're good to go from here now. You're highly welcome. Thanks for joining me here. I really do appreciate. Okay. I just feel like though this was my live session yesterday, that live class with students, but I actually want to do something different today. Just for those that is going to be sitting for the forthcoming JAMB exam. Yeah. Though since this diagram is already showing in my distance, but don't think we need it. That's not yours. But I will just say something. Yesterday I was teaching them what we called, I was on the topic. I've been on electrostatic few days now. That's we're on capacitors, otherwise known as condenser, which I told them is a device that stores what we call electrical charge. Yes, it's a device that stores electrical charge. And on that same note, we're able to do, you can see my board, so it's filled. So I told them a whole lot. But since my distance is already showing this, I can as well just say one or a few things. What I want to have here today is chemistry, actually. I want to just go through some questions to just for a few minutes. Now, I say that capacitor is a device that stores electricity, which if you see here, we have this arrangement of capacitor. This is it. That is two conductors body this way. Yeah, this let's say this is Q minus and this is Q plus. That is how conductors or capacitor is arranged, two parallel plates. So this gap is what we call the dielectric. The dielectric can be paper, it can be mica, it can be anything. You can see the dielectric. Now that will now give us, I want you to understand that the charge is always proportional to V. So that is number one thing that you need to understand. I don't want to really talk too much or say something that will not revolve around the point. So let me see if I can zoom it further. So now this dielectric is what we call the insulator body. And there's a reason why you put dielectric in a capacitor. It helps in a way to increase the capacity of a capacitor. Capacity of a capacitor, otherwise known as capacitance, is the ability of capacitor to store electrical charge. When you remove the constant of proportionality, you have that Q is equal to CV, where Q is charge measured in coulomb, as C is capacitance of capacitor or capacity, which is the ability of capacitor, which is the ability of capacitor to store charge. Then V is the potential difference. C is measured in farad, as V is measured in volts. So this become the formula. This is how it starts. Okay. And you also see there's another formula that C is equal to AE all over D. This answers questions about which the factor that capacitance or capacitor depend. As you can see there, it depends on area. It depends on area. How does it depend on area? It's directly proportional. And for the fact that it's directly proportional, what does it show? It shows that increase in area increases capacitance. And the same thing also depend on what we call this E. C is capacitance, so I said that already. A is area. E is what we call dielectric. Dielectric. Dielectric or relative permittivity. Relative permittivity. Permittivity. By permittivity, we mean the ability of the electrical line of force to pass through substance. That is what permittivity is all about. So it is called dielectric or relative permittivity. Dielectric or relative permittivity. That is what we call the C. Then moving on, I want you to understand that increase in dielectric, which is this material, this is it, this material that you are seeing is dielectric. This one that I put like a mesh. So it's the dielectric between the two conducting bodies or two parallel plates that constitute capacitor. And they help in a way to increase the ability of the capacitor to store charge. If you know that, I just want to maybe talk about the arrangement. Maybe we're done with this. Now look at this. Here, increase in A increases Q, increase in relative permittivity, otherwise known as dielectric, increases U. Are you seeing? But increase in distance between the parallel plate. You see, this and this capacitor will not have the same storage. Are you seeing? This one, the distance, this gap between this and this is the D. So the distance is too much. Are you seeing it now? Even though you put your dielectric, but increase capacitance. I don't want when they ask you simple questions, all those things. So you should be able to know what you are being asked at every particular point in time. Know what you are actually solving for, or the question, where the question is heading to. So those things will actually help you very well. So don't forget what I just said. For those of you that are here with me, are highly welcome. And thanks for joining me here. Okay. Thanks for joining me. All right, moving on. Let me just, like I said, this is not the essence of this. I just want to test something actually. But testing have led us to do all this. So you have understand some basic. This formula is very important. And at times, this formula, they will give you EM, meaning permittivity of the medium. There's a formula for obtaining EM. EM is known as E naught ER. Are you saying it now? Where this is what you call medium permittivity. Medium. This one is vacuum permittivity of free space. Vacuum, let me use vacuum. As this one is relative. I told you time before now. This one is called relative. That is why it's most in have face out. They have face out. Yes. What? Is that network? Is that data or what? No, no. Sorry. This network is bad. Oh God. Okay, just like I said, this is the basic thing that you need to have over there. And you see this one now, you got the capacitance of the medium given as this. So when you understand all this, then we proceed further to the next line of action, which will give us one or two hints on arrangement of capacitor. So which will give us one or two hints on arrangement of capacitor. So that is the first thing for you to take note of. So let's talk about the arrangement. At least I've been able to, without wasting time. It's not maybe short, small. Yes, I'm done with this. Now let me just tell you, capacitor can be arranged in parallel and also in series. Now let's talk about parallel arrangement. For parallel arrangement, no need to talk much. You can actually have something like this. So for parallel arrangement, so this parallel, let's say here is our point A, here is our point B. So this can be my C1, C2, and C3. And that is how parallel arrangement should be. Parallel arrangement. Please take note. Let me see. Okay. So that you see it perfectly well. Okay, that is how parallel arrangement will now be. Now look at this. Quickly without wasting time. In this, eh? In this particular arrangement, you see that they have same V. They have different Q. What do I mean by same V? They have same potential difference, but different charge. So with that, you can say that V total is your V1, which is also equal to V2, which is then same hand equal to V3. So let's call them V. They have same potential difference. So but charge now, the charge QT will be Q1 plus Q2 plus Q3. That is what the charge will be. So that is what the charge will be. Which when this occur, you see here, note that Q is equal to CV. So meaning our Q total, instead of putting QT, you just put what? C total V, since the voltage is the same. V total is either V1, V2, or V3. So it becomes equal to it becomes C1V plus C2V plus C3V. And you see, it becomes CTV equal to V into C1 plus C2 plus C3. So V against V. That will now be giving you, I'll clean it up after when I'm done with the parallel arrangement. I'll be giving you for parallel that C total equal to C1 plus C2. C2 plus C3. Just add your individual capacitors to get the distance. That is how it is. You add your individual capacitor Which when you do that, there are questions that you need to understand with respect to this display that we just did here. And number one question you see, as compared, that in terms of parallel arrangement, there are few things that you need to know. Number one, they have same voltage but different charge. And owing to that, you see that your C total or your charge is just, since it's different, total charge is equal to the summation of the individual charges, which depends on the capacitance of the capacitor. Are you seeing it now? Now, that aside, then you see this is now the formula that we arrive at to calculate the net capacitance or the equivalent capacitance. You use this formula, add the individual, add them directly. Unlike when we go to series, remember what happened in resistor. That is the opposite of parallel capacitor is equivalent to series resistors. So you should take note of that. So what are we saying in essence here? You see that when you are comparing, let's take for instance, for example now, if C1 equal to 2 microfarad and C2 is equal to 3, okay, let me say 5 microfarad. Now your C total in terms of series will be C1 plus C2, which will be 2 microfarad plus 5 microfarad, and that will be giving you 7 microfarad. Are you saying something? That will be giving you 7 microfarad. Now, when you are to compare the, if you are to compare the total, look at this, if you are to compare the total capacitance to the individual capacitor, you can deduce that the total capacitance is larger than the largest capacitor. What is the largest here? 5. 7 is not larger than 5. So CT is greater than C2, which is the largest capacitor. So there's no need of comparing it again to C1 that is even less than C2. So all these are some technical questions. There are times that will give you any values and all that, and you have to give them exactly what they are looking for. So you should take note and be careful with those kind of questions. Yes, take note and be careful with those kind of questions. I don't know whether if you have any questions revolving around what I just said now. If you have any questions. Okay. In the absence of no question, let me go to series. But don't be parallel now. Let's go to series. So let's go to series connection. Let's go to series connection. For series, they have same charge. Same charge. But different PD. That is different values of potential difference. Okay, so here, since PD is different, your V total is equal to V1. Is equal V1 plus V2 plus V3. Don't forget firstly that your Q total is equal to Q1, which is equal to Q2, which is equal to Q3, which you cannot say that is equal to Q. Yes, but they have same charge. It's for series. Then, moving on, don't forget that your Q is equal to CV, which will imply that V is equal to Q over C. So with this now, you see in terms of this, it becomes Q over CT equal to Q over C1 plus Q over C2 plus Q over C10. So that will give you that Q over Ct equal to Q into 1 over C1 plus 1 over C2 plus 1 over C10. So this against this, that will give you finally that 1 over C total for series is equal to 1 over C1 plus 1 over C2 plus 1 over C10. So that becomes the formula for calculating total or net or equivalent capacitance for that of series. That becomes the formula for calculating that for that of series. So there's a whole lot. It's just that, just like I said before, I'm going to come back fully here. Then we talk about what I was actually test running to see if it will be okay enough so that all my students will join me. So this is just a test running. But I don't just want to go not doing anything. So I want to still record a session. Let it be recorded that we have just few moments of interaction. I think when we see we do much more than this. Thanks for joining me here. I really do appreciate. At Favor, at Elijah Adie, and the rest of you that have been partly in and partly out. I appreciate from the bottom of my heart. Thank you very much. See you when next we meet. Bye.